Hello everyone, welcome back to Deeksha Karnataka YouTube channel, and today in the Masterstroke series I am going to discuss about a chapter, Nuclei. Now before I start that, a lot of concepts from this chapter are deleted, so if you are solving PYQs from any of the PYQ books available or from anywhere, be careful. There are a lot of questions which used to come from this chapter, radioactivity, and then some questions from nuclear fission or fusion, nuclear reactor related questions. Those are now deleted. Only very few selective concepts are still there in this chapter, but like atomic mass unit is there, okay, mass defect is there. So these are concepts are there, but other than that, from radioactivity there used to be a lot of question used to come from this chapter, but radioactivity portion is completely deleted, so there will be no questions based on radioactivity this year. Even if it comes, it will either be considered deleted, means they will either delete it or they will give you a bonus mark. So don't worry in case some question is coming from out of the syllabus portions. So definitely be careful. This is a semi important chapter. 2.5 question comes from this chapter. That means atoms and nuclei combined 5 question comes every year, so you cannot skip this, but as I think this year questions, maybe there will be at least one question from the mass defect portion, right? But before discussing everything, let us start with the list of important concepts from this chapter. So nuclei, obviously how nuclei is existing, then atomic mass unit, as I said, very important concept. Size of the nucleus is obviously another concept. Then nuclear binding energy, very important, and nuclear force. So these are the 5 important concepts from this chapter. We will learn everything in this one short video. So first of all, nucleus. Let us study about nucleus. Experiments on scattering of alpha particles that we did in our last lecture demonstrated that the radius of nucleus was smaller than the radius of an atom by a factor of about 10 to the power of 4. So size of the atom was 10 to the power of 10. That was known from the kinetic energy experiments, and nucleus was much smaller than that, almost 10,000 times smaller than the size of the atom. Okay, 10 to the power 4 means 10,000 times. Sometimes we do not realize how big or how small it is. 10 to the power 4 is 10,000 times smaller. Okay, so nucleus is very small compared to the atom. Now this means that the volume of nucleus is about 10 to the power of minus 12 times. So if we assume that it's a spherical surface, then volume will be 10 to the power of r square, r to the power cube. R to the power cube means 10 to the power 4 whole cube. So volume will be 10 to the power of minus 12 times smaller the volume of the atom. So it is very, very, very tiny. Okay. In other words, an atom is almost empty. So atom is almost empty, and at the center of the atom there located is the nucleus. If an atom is enlarged to the size of a classroom, the nucleus would be the size of a pinhead. So if you increase the size of the atom compared to your classroom where you are you take your notes in the PUC board exam, then the size of the nucleus will be just the size of the tip of this. You can imagine, as small as that. Okay, so very, very, very small, very tiny. Now very important part is atomic mass unit. Okay, atomic mass unit is what? Because the mass of an atom is very, very small, we need a new unit to express the atomic masses, because if you want to express it in kilograms, then it will be always be 10 to the power of something to the power minus, which makes it insignificant, as if that the value is not significant at all. But when you consider in terms of atomic units, they are very, very significant. So we have to define a new unit which only is useful for mass of atoms. Okay, mass of atoms, nucleus, protons, electrons, etc. Okay, so the unit was defined with respect to carbon 12 atom, and the value is given by 1 U. In old generation books it was referred as AMU, but all the modern books they only use U. U is for atomic mass unit. Okay, so this is called atomic mass unit, and one atomic mass unit is basically 1.66 into 10 to the power of minus 27 kilograms. Okay, you don't need to remember this value obviously, but what you have to remember, you have to remember this value, 31.5 MeV per c square. So what is the meaning of that? So if in many cases where you have to convert atomic mass into energy, that is very, very important. So when you convert atomic mass unit to energy, okay, only thing that you have to remember, if you multiply with this 931.5, then the energy would be in mega electron volts. Okay, so for example, if you convert 1 U of mass into energy, then the corresponding energy would be 931.5 MeV. Now sir, why you have given this divided by c square? Because when you convert say mass delta m to energy, then how can you convert into energy? You have to multiply it with c square. So mass can be written as energy divided by c square. Okay, this is a formula. Now this based on this MeV per c square is a common nomenclature. Here c square is obviously speed of light. You don't want to multiply with, always multiply with 3 into 10 to the power of 8 whole square with mass. So that is why this is a conversion factor, is very, very handy and important to remember its value. Same is to remember that you are preparing for KCET requires a lot of practice and lot of preparation. So Abhyas KCET test series is exactly that, where you will get 4 free tests which is already available. If you have registered yourself, you can access to that 4 test papers, and there will be 31 paid tests. It will start from 17th of March. Okay, if you are watching this video after 17th of March, then definitely you should know that Abhyas KCET test series is currently ongoing, and here you will get all the detailed video solutions and analysis of the question paper itself. You will get chapter wise one shot revision videos. You will get chapter wise insight for last 5-year KCET papers. So everything you will get at one place. You don't need to browse through YouTube, you don't need to browse through anywhere. Question papers, their solutions, live doubt solving, okay, everything you will get, and all inclusive the price is 1498. okay, if you purchase it now, 1498 is the price. So don't miss out on that. The price may go up, so don't forget to register yourself right now. Okay, now let's continue with our lecture, composition of nucleus. So what is the nucleus made of? So the positive charge in the nucleus is that of the protons. So positive charge that is located inside the nucleus is called protons. Okay, a proton carries 1 unit of fundamental charge and it is stable. Fundamental charge means, obviously we know that fundamental charge is E. Okay, charge of an electron, but electron's charge is negative, proton's charge is positive. Magnitude wise both are same. Fundamental, one fundamental means 1 E. Okay, 1.6 into 10 to the power of minus 19 coulomb. Charge of an electron is negative, charge of a proton is positive. That is the difference. What else? Neutrons are neutral but not stable. So neutrons are also part of the nucleus. They are neutral, but you have to remember that neutrons are not stable. So in amongst the nucleons, which one is not stable? Neutrons are not stable. Why? Because a neutron decays into a proton, an electron, and an antineutrino. Okay, so you don't need to know what is antineutrino is, what is neutrino is, but you should remember that a neutron does not stay a neutron throughout its life. Okay, it's very soon it decays into a proton, an electron, and an antineutron. Okay, antineutrino, sorry. Now this electron sometimes comes out of the nucleus, so people think that nucleus contains electrons. Actually not. In nucleus free electron is not possible. Due to the decay of neutron, electron can be generated, and that electron can come out of the nucleus, but that is not a nuclear electron. Okay, electron does not exist inside the nucleus. Okay, nucleus does not contain electrons. Very, very important. Even though, as I said, in some cases you will see nuclear electrons. For example, beta decay. In beta decay, the electron, this is a kind of electron coming out of the nucleus. So initially people thought nucleus also has electrons, but later on it was discovered that this is because of neutron is decaying. Because of that, electron is coming out, and that has nothing to do with nuclear electron. Electron does not exist inside the nucleus. Now next, the composition of nucleus can now be described using the following terms and symbols. Very, very important to remember. Z is called atomic number, number of protons. So what is the meaning of atomic number? Atomic number means it is the number of protons. Okay, next is neutron number, number of neutrons, obviously, and the mass number is Z plus N. So total number of nucleon is represented by mass number. Nucleons means the constituent of the nucleus. They are in short called nucleons. Okay, so mass number represents total number of nucleons. Even though the term says mass, it does not always actually represent the mass, even though it is proportional to that. But mass number does not always represent the mass, but it is very important because only neutron and protons constitutes the nucleus. So obviously if you say mass number, that means it represents the total nucleons. And symbol for nucleus is represented by AZX. A is mass number, Z is proton number, and X is the symbol for the metal. For example, here we have taken AU. AU is for gold. Gold, obviously we know that 197.79. Okay. So from here you can even calculate what is the number of neutron inside. Even though mass and proton number are given, you can calculate how many neutrons are there by doing the fact that 197 minus 79. If you do that, you will get the number of protons inside it. It will be not 6. Neutrons are there inside the nucleus. So this is the number of neutrons, right? And what else? It has been found that the nucleus of mass number A has a radius of r equals to r naught e to the power 1/3. A is the mass number. Obviously, if the mass number is A, then the radius of the nucleus is given by r naught e to the power 1/3. What is r naught? R naught is 1.2 femtometer or 1.2 Fermi. Okay, and also you have to remember that the volume of nucleus is constant. Density of the nucleus is constant. Why? Volume is 4/3 pi r cube, and density is volume by mass. Okay, mass per volume, mass per unit volume. Mass is proportional to mass number, so A divided by volume. Now r cube means what? R cube means obviously it will have r naught cube 4/3 pi r naught cube into A to the power 1/3 cube, that is only A. So you will get that density of the nucleus is constant. It only depends on r naught. It does not depend on anything else. R naught is a constant, so density of nucleus is constant. Now let's see one question. A nucleus at rest splits into two nuclear parts having radii in the ratio 1:2. Their velocities are in the ratio. So first of all, a nucleus was at rest. Okay, even though it is not directly related to nucleus, but okay, let's see. So nucleus split into two halves. One has a radius 1. So after splitting, obviously it split into two spherical objects, right? One has a radius 1, another one has a radius 2. Okay, and their velocities are in the ratio. So how can I find velocity when nothing else is given? So to solve this, first of all you have to remember that nucleus was at rest. That means once it is splitting into two parts, the linear momentum has to be conserved. So m1 v1 equals to m2 v2. That is, after the split, whatever their velocity will be, that will be given by this relationship, m1 v1 by m2 v2, or v1 by v2 is equal to m2 by m1. Okay, now what is mass? Mass is density into volume. Mass is density into volume. Now density, as I said, nuclear density is constant, so density will cancel. You will get V2 by V1. Okay, V2 by V1, because densities are constant for nucleus. Now if you write the volume, it will be 4/3 pi R2 cube divided by 4/3 pi R1 cube. 4/3 pi cancels. So what is R2? R2 is 2, so 2 cube is 8 and R1 is 1 cube, that is 1. So their velocity is V1 is to V2 will be equals to 8 is to 1. Okay, so even though no data is given here, only data you need to know that mass is basically proportional to volume, because density is constant. So from there you need to just find the ratio of the densities. Okay, so it will be 8 is to 1. So even though the problem seems difficult, actually it is very simple. Obviously this kind of ratio related questions sometimes can be tricky, but if you know the answer, you know the process, or if you know the theory, you can answer such questions. Now let's move on. Mass and energy. Einstein's famous equation is E is equal to mc square. Here the energy equivalent of mass m is related by the above equation, and c is the velocity of light in vacuum and is approximately equal to 3 into 10 to the power of 8 meter per seconds, right? Now we have seen that the nucleus is made up of neutrons and protons. Okay, therefore it may be expected that mass of the nucleus is equal to the total mass of its individual protons and neutrons. Okay, however, the nuclear mass m found to be always less than this. Okay, this difference in mass is called mass defect. So what you are expecting, that I always give you one example, even in your PU board exam as well, that you went to a market. Okay, you brought 10 apples, 10 oranges. Okay, 10 apples, say 2 kilogram apples, 2 kilogram oranges. Now if you take a bag, you put 10 apples, 10 oranges, okay, and you measure the weight, what you are expecting? So 2 kg apples are there, 2 kg oranges are there, 10 number is 10 and weight is 2 kg, mass is 2 kg. Now if you put them in a bag and if you measure them, what you are expecting? You are expecting that the bag is to weigh 4 kilograms, right? So that was our expectation. Same thing we are expecting in case of nucleus. Now nucleus is very weird, unlike the shopping market where you actually get 4 kg means 4 kg. But if you do it same things for nucleus, instead of getting 4 kg, you will get say 3.8 kg. So what happens to 200 gram of nucleons? Suppose you took 2 kg of protons, 2 kg of neutrons, okay, and you mix them together in a bag, pack them in a nucleus, and if you try to measure the mass, then that mass will be less than whatever elements are there inside, which is very, very weird, right? So this 200 grams of missing object actually gives rise to the nuclear energy or nuclear binding energy. Okay, so what is the formula for that? So this is called mass defect. This difference in mass is called mass defect. So this is 2 kg of protons, this is 2 kg of neutrons. You put them together and when you measure their mass, you find this to be 3.8 kg. So this is the formula, very easy formula. ZMP plus A minus Z, Mn minus M is the mass defect. And if you want to break the nucleus into its constituent protons and neutrons, the extra energy delta mc square must be supplied. This energy required is related to the mass defect by EB equals to delta mc square. This is called binding energy, obviously. Okay, and this is called binding energy. And as the name suggests, it obviously binding the nucleus together. So because nucleus is a stable thing, it does not break apart easily, so that energy actually keeping the nucleus together. Now binding energy per nucleon, if you divide this energy by total number of protons plus neutrons, that is mass number, if you divide the energy by mass number, you get binding energy per nucleon. Per nucleon means, so you are in a classroom, okay, you have say chocolates are distributed, you have say 100 chocolates and 50 students in the class. Then what is the number of chocolates per student that you can get? So number of chocolate means total number of chocolates divided by number of students, that you will get 2 chocolates. So that is the binding energy per nucleon. So how many energy they have per nucleons. This is very, very important. The mass defect of helium 242 is 0.03 U. The binding energy per nucleon of the helium in MeV is. So how to do that? Very easy. 0.03 U is given. So this is binding energy. So binding energy is basically U into, first you have to convert it into MeV 931.5 MeV. This is the binding energy, and how to calculate, convert it into binding energy per nucleon. EB equals to 0.03 into 931.5 divided by 4. Okay, divided by 4. Now how to calculate this thing? It seems to be very difficult, right? So there are 2 ways to do it. First of all, because we are doing approximation, we can consider this 931 is either 900 you can take, or you can take 1000. 1000 will be easier, at least in this case. So based on case to case, we can take the approximated value. Okay, obviously we have increased the value here, so whatever calculations we will get, the actual result will be less than that. Okay, so 250 is the value. Now that will be 3 into 0.25, 7.5 that we received. So 7.5 MeV. Now obviously because we have increased this value, actual value should be less than that of 7.5. Now which is less than 7.5 here? 6.9 fits perfectly into our calculations. Okay, because 7.5 we have increased 931.5 to 1000, so that we can easily cancel this. Okay, so here the result should be 6.9825. okay. Now let's move on. Binding energy per nucleon versus mass number graph. Okay, so this is the binding energy curve or binding energy graph, whatever you say. So as you can see that binding energies keep on increasing up to some point, then it becomes highest for iron. Fe has the highest binding energy per nucleon. Okay, this is binding energy per nucleon, not the total binding energy. Okay, and you see that the binding energy graph getting flatter, so it is increasing, it is not keep on increasing. After some time it getting flatter. That means change is very small in this region. Okay, in this region if you see, the change in the binding energy graph is very, very small. Okay, so it is changing. It is changing about from 7.8 to 8.9, almost 9. It is changing by 1 to 2 EV, but 1 to 2 EV is smaller compared to 1 to 8 EV, right? So the change is very small, so we say that it is practically constant. So binding energy graph is almost constant, but you have to note 2 things. What are those 2 things? First of all, the nucleus, lighter nucleus, these are lighter nucleus, right? Their average binding energy per nucleon is far less than the higher mass. Okay, and it is keep on increasing. Similarly, heavier nucleons, they also have a binding energy lower than the middle table. Okay, not the lightest one, but from the middle of the table, whoever you see, all the elements have higher binding energy per nucleon compared to these heavier nuclei. So heavier and lighter, both nuclei have less binding energy per nucleon compared to the middle of the section. Now, let's see. So features of the graph, very important. The binding energy per nucleon is practically constant, that is independent of the atomic number for middle region of the graph. So in the middle region of the graph, as I said, the variation is very small, so it's practically constant. Okay, and it does not depend on the mass number. Next, EVN is lower for both lighter nuclei A less than 30 and heavier nuclei A greater than 170. Okay, a very heavy nucleus, say A equals to 240, has lower binding energy per nucleon compared to that of a nucleus with 120. So this one is a heavier nuclei. Its binding energy per nucleon is smaller compared to binding energy per nucleon of A is equal to 120. So if this nuclei breaks into two smaller nuclei to attain more stability, everyone wants to attain more stability, right? So binding energy per nucleon was smaller for A is equal to 140, but when it reaches to A is equal to 120, that means binding energy increases. So if binding energy increases, means you can consider this to be the extra energy is released into the atmosphere. Okay, so thus nucleus A is equal to 240 breaks into two 120 nuclei. Nucleons get more tightly bound, so their binding increases. This implies the energy would be released in the process. This is known as fission. Okay, fission means atomic bomb. We'll see fission in detail as well. Atomic bomb, nuclear power plant, they are the common example of nuclear fission. And consider two very light nuclei A less than 10 joining to form a heavier nucleus. The binding energy per nucleon of the fused heavier nuclei is more than the binding energy per nucleon of the lighter nuclei. This means that the final system is more tightly bound than the initial system. This process is known as fusion. Fusion happens inside the star. Okay, now if you may have heard that in case of star, that highest possible element that can form inside the star is iron. Okay, iron is the last stage. When the star is about to die, the iron is formed inside its core. That means it cannot fuse anymore. Why? Because iron has the highest binding energy per nucleon. So this is the most stable element. Okay, so this is the most stable element. Any stable element does not want to go to a less stable element. If you merge or if you fuse to iron, somehow if you are able to fuse them to get heavier nuclei, you will not possibly get that because it is the most stable nuclei. Okay, so any energy cannot bind to iron together because it is already attained the stability. So that is why stars cannot produce more than iron. So star starts with a lot of hydrogen. Okay, hydrogen starts fusing, then they forms helium. Okay, helium also fuse. Okay, after helium is fusing with hydrogen. Helium can fuse with another helium. They forms lithium, they forms nitrogen. Okay, all the elements in the periodic table are formed till iron. Okay, and this last stage happens quite fast because initially when it starts with a lot of hydrogen, okay, hydrogen dominates everything. Slowly helium also comes into the picture. Right now in our sun, obviously not everything is hydrogen. There is a sizable part of helium as well, and other elements, lithium, nitrogen, oxygen, etc. Everything is present there. Okay, it is happening there. So they are fusing, but the quantity is very low compared to hydrogen, obviously. So once the hydrogen fuels keep on burning, it is the pressure of the hydrogen is no longer sustainable. It starts fusing into the heavier elements till iron is formed, and then it bursts. Okay, depending on the size of the star, it can get different results. Okay, now astronomy, this is not an astronomy class, so I'll move on to the next part, nuclear force. So to bind the nucleus together, there must be a strong attractive force. So we are talking about binding energy. Now let us discuss about force. So nucleus obviously there are lot of positive charges are there, protons are there, okay, not only hydrogen, there are heavier elements, right? So for example, iron has a lot of protons present inside it. We have taken the example of gold has 79 protons present inside it, and they are tightly bound in a very small area, very small. We have learned that the size of the nucleus is very small, right? So how it is possible? Because in case of Coulomb's law, we learned that Coulomb's law states that the force is basically K Q1 Q2 by R square. Now in case of nucleons, the distance r is in the femtometer range, that is 10 to the power of minus 15 range. So square of that, and then 10 to the power of minus 15 in the denominator means it will be 10 to, square in the denominator means 10 to the power of 30 in the numerator. That means the repulsive force will be huge, 10 to the power of 30 range, right? Q1 Q2 is obviously smaller, but still the force is very, very high when the distance is very, very small. So the Coulomb force tend to take the nucleus apart, but why the nucleus is still sticking together even though the Coulomb force is saying go away, you are not supposed to be here? So that is because there is a stronger force which is keeping the nucleus together. That force is called nuclear force. Nuclear force is the force which is keeping the nucleus together, and it is different than that of the all known forces. For example, Coulomb force, gravitational force, they are not like this, okay? It is a completely different kind of force. Okay, the nuclear force is strongest force in the nature. We have studied properties of nuclear force. Nuclear force is the strongest force in nature. It is sometimes called strong nuclear force. There is another force called weak nuclear force, or only weak force. But nuclear force is called strong nuclear force, and that signifies it is the strongest force in nature. Okay, nuclear force between neutron-neutron, proton-neutron and proton-proton is approximately same. So in case of Coulomb's law, we learned that neutral objects does not have any kind of forces, whereas positive charges repel, negative charges attract, right? But in the case of nuclear force, even proton and neutron, even though they are neutral, they tend to exert nuclear force on each other. Okay, so nuclear force is independent of charge, or it does not depend on the electric charge. So nuclear force is independent of charge. Next, nuclear force between two nucleons falls rapidly to zero as their distance is more than a few femtometers. So for example, if a nucleus, I have a proton, I have suppose a proton, a neutron, another proton, okay, another neutron, another proton. So it is said that the nuclear force is strong when the nucleons are close, but there is no nuclear force between these two or these two. Okay, as you increase the distance, nuclear force falls rapidly to zero. That means it becomes zero. Okay, so nuclear force is almost zero for this. Okay, so Coulomb force is still there, but nuclear force is there, not there. But nuclear force between this and these two are very, very strong because they are very close. Okay, so here is the diagram of the potential energy. So you have to remember the diagram. There was once a question based on this diagram, that you have to remember that the potential energy becomes negative, and at some distance it becomes smallest. So smallest means up to this point it is attractive, after that it is repulsive. So up to this point the nuclear force is attractive, then it is getting equal to the Coulomb force, and then Coulomb force dominates. After some time Coulomb force dominates. So they are not sticking very close to each other, they are not going away from each other as well. Okay, so both forces are getting balanced. So whatever the nuclear force is, it is keeping them together. Also it is balancing the Coulomb force inside the nucleus. Okay, now radioactivity, that is to be now we will complete radioactivity in only one one part, but radioactivity used to be a very long concept, and based on that a lot of questions used to come. So as I said, radioactivity is now deleted, so don't worry too much about radioactivity now. While solving PYQs, be careful, don't waste time on solving radioactivity related PYQs. So radioactivity was a nuclear phenomena, is a nuclear phenomenon in which an unstable nucleus undergoes a decay. This is referred to as radioactive decay. So what is the meaning of unstable nucleus? So as we have seen that as we are going in the binding energy graph, as we are going heavier and heavier nuclei, the graph becomes lower and lower. That means the binding energy per nucleon is decreasing. But there is a tendency for atoms that they want to or mainly nucleus, they want to attain the highest possible binding energy per nucleon. If the binding energy is decreasing, then immediately they will emit something, they will emit some energy, they will break apart, and they will become stable. That means their binding energy per nucleon will increase. Now how it is happening? It can happen in three decays. What are the three decays? Alpha decay, in which a helium nucleus is emitted. So the radioactive substance will emit a helium from the nucleus itself. That means it will emit 2 neutrons and 2 protons from it, okay, and they are coming in a together pack. So together pack means it is considered to be a helium, okay. So that is coming out of the nucleus, making the existing nucleus lighter. Lighter nuclei generally have higher binding energy per nucleon, so they become stable, okay. Also there is another type of decay, beta decay. Beta decay, I told you, beta decay is basically when a neutron breaks down into proton and electron, and the electron comes out of the nucleus. That electron is called beta decay, okay. Which electrons or positrons, sometimes positron can also come out of the nucleus. Now what is a positron? I will tell you later. So positrons are, not later, let us discuss now. Positrons are particles with same mass of electron. People sometimes confuse with positron and proton. Positrons basically considered to be antiparticle of electron, okay. What is the meaning of antiparticle? Antiparticle means same mass but opposite charge, okay. So if you consider a negative proton is a antiparticle of proton, okay. Now negative proton is obviously not possible always, but electron and positron are possible, and when they mix together, okay, when electron and positron mix together, they gives rise to energy, okay. So whenever the universe was created at the beginning, okay, we know that it started with the Big Bang, and Big Bang was basically production of energy. From energy everything is created, and that energy, whenever some matter is created from energy, it generally creates some particles and their antiparticles, okay. So that is a beta decay. Gamma decay, high energy, hundreds of keV or more, photons are emitted. So gamma decay is when the nucleus itself emitting a high energy radiation from inside, okay, and gaining stability, okay. So these are the three types of decay possible in radioactivity, okay. Let's move on. Nuclear fission, okay, fission, okay. So when a heavy nucleus is bombarded with other nuclear particles such as proton, neutron and alpha particles, etc., it breaks into smaller stable nuclei and called daughter nucleus. So what is the difference between fission and radioactivity? Okay, fission, nuclear radioactivity is a natural process. It is happening everywhere in the world. It is happening even if your body, it is happening as well. Radioactivity is happening all the time. For example, when we inhale a radioactive sample of carbon-14. Okay, it comes into our body, it goes into our bones, and then it slowly stays there, and then it slowly radiate, okay. Similarly, a tree that also takes carbon from the wild, it contains carbon-14, and as long as it is alive, it is depositing that carbon-14 into its body, Okay, once it dies, okay, it is no longer accumulating any more carbons, okay, and then it is slowly the carbon 14 only decays from there. That is how we can determine how old a tree is. Carbon 14 takes a very long time to decay, so even 10,000 10,000 or 1 million years, we can still find that how much carbon deposit should have been into it and how much is left in it right now. Okay, so we can determine how what is the exact age of the tree. It is possible for humans also by checking the bone construction, how developed is the bone or how many rings are there in a tree. So based on that we can determine, okay, the tree should be 100-year-old tree when it died. So 100-year-old tree, how much carbon it should have accumulated during its lifetime, that can be calculated. So say 100 grams of carbon 14 accumulated in the tree. But when we are measuring right now, we are seeing that only 50 grams is left. So 50 grams left means 50 gram of carbon 14 decayed throughout the time. Now how many times, how much time is taken for decaying one carbon atom? Based on that you can determine how old is the tree. Now those calculations were part of your syllabus, but right now they are deleted, so carbon dating part is not there. Anyway, so this is the process. And fission, the difference I was talking about, difference between fission and radioactivity. Fission is when it is mostly artificial. When you bombard the neutron into an uranium, okay, uranium breaks into beryllium and krypton. Okay, so these are the two stable nuclei. They attain stability, and also during the process a lot of energy is emitted as a byproduct. Okay, so this energy we utilize either for destruction or for construction in both cases. Okay, so for example, if you do it in an uncontrollable way, it gives you the nuclear bomb. If you do it in a controllable way, you are getting in a nuclear power plant. Okay, so power plant produces energy through this method. Okay, what else? The fragment products are radioactive nuclei. They emit particles in succession to achieve stables. So these are also not super stable, they are radioactive. So they emit particles, they emit alpha particles, beta particles and gamma radiation. So after some time it becomes stable. Okay, but it is a long process. That is why the nuclear fuel, once it is used, they are stored in a secure process so that the energy released by the radioactive process does not harm anyone. Okay, radioactivity is not super helpful for our body. All the radiations not always is helpful. Okay, but okay, it is necessary. Next is the source of energy in nuclear reactors which produce electricity is nuclear fission. The enormous energy released in an atomic bomb comes from the uncontrolled nuclear fission. So as I said, if science is used in a controlled way, it is constructive. If you use the same science in uncontrolled way, it can be super destructive. Okay, so always whenever you are doing some study in future, okay, always try to use science constructively. When two light nuclei fuse to form a larger nucleus, energy is released since the larger nucleus is more tightly bound. So same example I am giving you. I told you previously also. Here one example they have taken: two hydrogen atoms. Okay, under the heavy pressure, it can fuse into deuterium. Okay, deuterium is a isotope of hydrogen. Okay, and it gives you one positron. E plus represents positron. Okay, so E minus is electron, E plus is positron. Nu is the radiation, and also sorry, this is neutrino, not radiation, this is neutrino, and nu bar is antineutrino. Okay, 0.42 MeV is the energy that is released in this process. Now in the stars, they use similar process to produce energy. For example, 4 hydrogen and 2 electrons, they fuse together to form helium, neutrino, gamma radiation and some heat. Okay, gamma particle, neutrino and a huge amount of heat is being produced, 26.7 MeV, and this gives rise to more fusion. More fusion means more energy generation. So here in the stars also you can say fusion is somewhat uncontrollable, but because of the enormous mass and enormous gravity basically controls how much should be fused inside the stars. Okay, as long as there are a lot of factors, stars is a very complicated system, and if you want to study them in future, you have to study more astrophysics and become an astronomer, right? And now if you want to learn more from our channel, then definitely you have to subscribe to our channel if you have not yet subscribed. I'll be back with a new Masterstroke lecture very soon. Till then, bye.